Okay, so I want to do a video on Taylor series right now. And I'm going to start with this game called the Magical Mystery Function game. And I think it lays down the foundation. Taylor series are confusing, even in a normal year, even when we're all in the same classroom together. And you can ask me a question the moment you get confused. Taylor series are still difficult. And they're going to be even more difficult this year, I suspect. But let's play this magical mystery function game, which really, this is definitely not the right way to play the magical mystery function game because this is a one-way stream of information. Any game is meant to be played in real time, live with other people. But I'm going to tell you that I've got this magical mystery function, and I don't know exactly what it is, but it is a polynomial, and I'm going to give you some derivatives. And I'm going to tell you that f of 0 is equal to 6, f prime of 0 is equal to 4, the second derivative at 0 is equal to 2, and the third derivative at 0 is equal to 48. And let's just say, there's a bunch more of these. Well, let's start right here. Let's say, what would f of x be? Well, you might start by thinking, well, f of x is going to be 6 plus 4x plus 2x squared plus 48x cubed. And if you think about this, this is sort of potentially what will happen. What happens when you take the first derivative of this? F prime of x is going to equal 4. What's going to happen when you take the second derivative? Wait, sorry. It's not equal to 4. What happens in this, when I take the derivative, f prime of x, it's lengthy. But if I'm only looking at it at 0, there's only one term that matters, which is this term. Because the other terms I'm going to still have an x, and I'm going to plug in a 0. This term is going to become 0. So f prime of 0 is equal to 4. And if I think of what's the second derivative at 0, well, that's actually going to be 4 times 2. If I think of what's the third derivative at 0, that's going to be 48 times 3 times 2. Notice another way of writing this could be times 3 factorial. So how am I going to compensate to make my magical mystery function the correct one? Well, I actually have to, and this is something that ideally you would sit and be confused about for a minute and then see that the right thing to do in this situation is put 1 factorial under here, 2 factorial under here, 3 factorial under here, go all the way up, and this would be a times x to the n divided by a factorial. In a perfect environment, you'd be able to stay confused a little bit more. In this environment, just have to rush through these. But you'll see a lot of times going forward, because there's going to be a lot of other things, a lot of other pieces that are tied together. And then at the very end, it's like, oh, and you have to put in that little factorial thing. That's where the factorial thing comes from. So close your eyes and close your eyes real hard so that you feel your eyes closing and your muscles are almost cramping up. You're clenching them so hard, and try to tell yourself that when you wonder where that factorial came from, it's from that feeling, and have that feeling remind you of that thing that I just taught you. All right, so let's do an example now where we're going to build a polynomial function to approximate something that we know is not a polynomial, cosine of x. How would we want to start doing that? Well, first thing is we want to have it a center somewhere. So we're going to center this at 0, okay? And so what would we want that function to look like? Well, we would want, for one thing, we would want the value at 0 to equal cosine of 0. So f of 0 should equal 1. What we would also want would be the derivative. The derivative of the function, if it's going to be approximately right, is going to look approximately like the function that we have, which is f, like the slope is going to be approximately the same as the function, which in this case is 0. There is no, the first derivative is 0. So if I'm building it, I'm going to get y is equal to 1 plus 0x. The second derivative is going to be negative cosine of x. The second derivative at 0 is going to be negative 1. So this is going to be minus x squared. And here's where I have to put in the 2 factorial, because I want the second derivative to be the same thing. When I take the derivative and then the derivative again of this, I'm going to have a 2 as a coefficient in front of that term. If I think of the third derivative, what's that going to be? Negative sine of x. What's the third derivative? F at 0 is equal to 0. If I think of the fourth derivative, that's going to be cosine of x. And if I think of the fourth derivative at 0, that's going to be 1. So now I get plus x to the fourth divided by 4 factorial, dot, dot, dot. Now I can think of, this is a pattern, and this pattern gives me an approximation. And let's see how this pattern does. You can see, I think, and trust that it's going to go in a repetitive fashion. Let's just say y is equal, well, let's go f of x is equal to cosine of x. And let's say g of x is equal to 1 plus, what was it, 1 minus x squared divided by 2 factorial. You can start to look at, where does this do a good job? Okay, and you can actually see that there are, for a lot of this picture, it does a really good job. Where it doesn't do a good job is when you start to get further and further away from the center, which in this case is 0. If you wanted to think of what is the error, like a lot of times you might see, use a second degree Taylor polynomial to approximate the cosine of x at, I don't know, what number is this? 0.75. So f of 0.75 is 0.731, 0.732. G of 0.75 is 0.7185. So the error, if I want to find the error function, or well, maybe not the error function, but the error value, I could say E of 0.75 maybe is equal to this number minus this number. Or 0.013. Did we do good? I think we did pretty good. Watch what's going to happen as I start adding terms, x to the fourth divided by 4 factorial. It starts getting more and more accurate, which is pretty cool. Let's think of, how could I do this so that I can keep going? Let's go, n goes from 1 to a, maybe. And what is this is going to be? Negative 1 raised to the n times x raised to the 2n divided by 2n factorial. And then I think this ought to work now when I get rid of this. And maybe I want to change the colors a little bit so there is a distinction between the two. Then I go like this, and it starts to get better and better and better. Go from 1 to 100, step 1. And I think at some point it's just like kind of breaks the bank, and it doesn't. At some point, Desmos gets slow, and it takes a while for it to catch up. But you could see from before that this does a really good job of approximating this polynomial as A increases. And that's the idea of a Taylor series polynomial. I think a Taylor series, you'll see Taylor and you'll see Maclaurin. You can sort of think of them as the same. A Taylor series is any polynomial approximation for a non-polynomial function. A Maclaurin is specifically one that's centered at 0. Most of ours are going to be centered at 0, but not always.